look at sample problem 33.5. The problem consists of the following. You have a very thin copper strip in this fashion. This copper strip is of width A. This is A. It carries a current I throughout the width of the strip. We are interested in calculating what is the magnetic field produced at a point P that is located at a height capital R from the strip. So if I were to draw a cross section of this particular strip, it would look like this. This is the thin copper strip. This is of width A. Then we are interested in calculating the magnetic field at P. This is at a height capital R and which is located at the center of this strip. So therefore this looks like this. This is the center of the strip. P is a point here. This is capital R. Now how do we proceed with the calculation? Consider a very thin strip. Let us say this is a thin portion of the strip. This is located at a distance x from the center. So this is x. So if I were to show it in the cross section like this, this would be the thin strip. This is at a distance x. Now let us complete this right angle triangle. Let this distance be small d. Then let the thickness of this, that is the width of this small strip, be dx. Let the width of the small strip be dx. So this whole width A can be treated as infinite strips of width dx, dx, dx and so on and so forth. Now if I is the current throughout this width, then the current per unit width is given by current per unit width is I by A. Then the current through only this dx will be given by I by A into dx. So therefore what we have reduced is, we have reduced the whole copper strip into multiple thin strips. Now we know what is the magnetic field produced by a straight wire at a point P, and that is given by B equal to mu 0 I divided by 2 pi d, where this d is the distance of the point P from the wire. That is why we have used this d. So let us apply this formula to this small portion of the whole copper strip. So therefore this will be mu 0 I, but this I is nothing but whatever I is flowing through this small red portion. So this I can write it as mu 0 I, which is nothing but I by A into dx. I hope it is clear. Now if you notice that this magnetic field produced by this wire at point P, so this is point P, this is point P, will be in this particular direction. Because if the current is flowing in this direction, then the magnetic field lines will be circles, and if you at this point, if you draw the tangent, it will be in this direction. So you can resolve this into two components, this horizontal component, and you can resolve this into vertical component. Notice that for every small dx here at a distance, there is exactly same another dx at this point, that is here. There is another. Now what is the magnetic field produced by this strip? If you are to draw circles, go on and go on magnetic field lines for this, you will notice that a circle will pass like this, and if you were to draw the tangent, it will be pointing in this direction. Again, you can resolve this into horizontal and vertical components. You notice that this is exactly of the same magnitude but opposite in direction to this, and therefore will cancel. The net effect will only be in this horizontal direction given by this red arrow. So let's do that. I forgot to put a small d of b indicating that this is the magnetic field produced by a small portion. And now let us further, I hope I have convinced you that only the horizontal components will be contributing. So let us take this angle to be theta. This angle is theta. This angle is also theta. And if this magnetic field is dB because of this strip, then only the horizontal component dB cos theta will contribute. So therefore dB cos theta is a contribution because of this. So let us substitute what is dB. dB is nothing but this. Therefore dB horizontal, I'll give a new symbol for this dB horizontal, is given by d of b into cos theta, mu 0 I dx by 2 pi a into d cos theta. Now let us do one thing. Let us replace what is d. What is d? You can notice that if this angle is theta, cos theta is nothing but cos theta is equal to adjacent side divided by the hypotenuse, or d equal to r by cos theta. So let us substitute in this. dB of horizontal equal to mu 0 I dx cos theta 2 pi a, d is nothing but r by cos theta. This cos theta goes to the numerator and gets multiplied. So therefore this becomes dB of h equal to mu 0 I dx cos square theta divided by 2 pi a into r. Now if I integrate this for the whole strip, I will get the contribution for the magnetic field because of this whole strip. So let's do that. Let me write this. Integral d of bh is equal to total b. So therefore b equal to mu 0 I divided by 2 pi a r integral d of x divided by secant square theta. I have brought this cos square theta to the denominator, therefore it has become secant square theta. Now let us change the variable of integration to that of theta, that is dx. Now let us go to this angle, this right angle triangle. You can notice that tan theta is equal to opposite side divided by the adjacent side. Therefore x equal to r tan theta, or d of x is equal to r secant square theta d theta. Substitute this into this, you get b equal to mu 0 I by 2 pi a r integral r secant square theta d theta secant square theta. Secant square theta cancels. This r comes outside the integral, cancels with this. Therefore we are left with mu 0 I 2 pi a into d theta. But what are the limits of theta? Notice that this is the maximum angle that theta can take. So you can take all the way. Let this maximum angle be plus alpha, and similarly this is the maximum angle, this is minus alpha. That's the reason for calculational simplification we have chosen P to be exactly at the center of this whole copper strip. So if this is alpha, so I hope I have convinced you theta can take from minus alpha all the way it goes up to plus alpha. So let's perform this integral, you will get mu 0 I 2 pi a. D theta integral is theta. If you substitute upper limit and lower limit, you get 2 alpha. 2 cancels, so therefore we have b equal to mu 0 I by pi a into alpha. But what is alpha? Alpha is, if you look at this complete triangle, if this is, that is up to here, this is the maximum angle alpha, then tan of alpha is equal to opposite side. But if this total width is a, then this will be a by 2. So therefore we get tan alpha equal to a by 2 r. But alpha equal to tan inverse a by r, so therefore b equal to mu 0 I by pi a tan inverse a by 2 r. Now let's look at a limiting condition, that is, as this r becomes larger and larger, what happens? As this r becomes larger and larger, then tangent can be replaced by the angle itself. So therefore you get b equal to mu 0 I pi a by 2r. A cancels, so therefore we have b equal to mu 0 I divided by 2 pi r. This completes sample problem 33.5.